This is the lecture for Class 9 Suitability Analysis, and this is another model in GIS that can be utilized to find, quote, suitable locations, and it's a good model to use for final projects for the course also. So let's get started with a quick review of Class 8. In Class 8 we were working with OpenStreetMap as a participatory mapping platform, and we talked about where OpenStreetMap happens, and we talked about the Web 2.0 as the point in time in web development where the notion of crowdsourced data and having individuals contribute their own data to the web became paramount. We talked about OpenStreetMap as being open, so the data we can both produce ourselves collaboratively with other people or just alone. And we can also utilize that data for other purposes. So we can make our own maps with it, we can download it for further GIS analysis in a desktop GIS, many things we can do with it. Other platforms, they're closed systems and they're proprietary, and they're certainly not going to let you have that data without paying them. We talked about the format of OpenStreetMap, that it comes to us in a consumable format through a web browser in terms of tiles, and tiles are basically little images of a larger data set. And what's really important with tiles is the level at which we're viewing the map currently. So we can zoom in and out based on our level, and the level will determine which tiles are being pulled by our browser instructions to the server. We talked about the OpenStreetMap toolchain, that it's a series of processes to get to the final map, and we talked about a slippy map and how that performs. So this last week we went through each stage, producing data in the editor. We sent it to the database, and then from the database behind the scenes it was rendered so we could actually view that data. Our government's involved with OpenStreetMap through the hot mapping platform and this program called MapGive. And many players in the humanitarian development fields and emergency response fields, they realize the power of OpenStreetMap as an open mapping platform where data can be, geospatial data can be shared without licensing restrictions, and can be utilized for many different purposes, both GIS analysis but also simply just routing from place to place for emergency response. We're going to talk about suitability analysis. This term suitability analysis, we're going to describe what that is and how we can use it in a GIS. And going back to our first week's lecture where we talked about stacking of layers in the GIS, that principle becomes really important this week. We need to make sure that when we're doing any type of suitability analysis that we're in the correct coordinate system. So every file that we're working with, every raster, vector, whatever it's going to be, needs to be sitting in this stacked arrangement, this cartographic model. And the reason that we need to do that, especially for rasters, is that the cell location from one raster to another raster becomes critically important. So when we're doing processes, and this week we'll be using a raster calculator to actually calculate the values from one raster to another, what really becomes paramount is where the cells exist in terms of a coordinate space. So where the cells overlap, that's where the actual processing is taking place. So we don't want to think about the raster layer as a whole per se. What we're really interested in is where the cells lie and the calculation from one cell in one raster to another cell in another raster. That's the unit by which our calculations are taking place. We're going to start thinking in terms of a flowchart this week, so we're going to have a start and a finish point. Up to this point in the class, we've really been doing things in a desktop GIS where we do one step and we save it, and then we do some other steps, and they kind of don't seem really connected to each other. So with a flowcharting scenario, we can think of where we start and where we finish, and we can visually see that process taking place. And when we do this, we do it in an environment called the Model Builder in ArcGIS, and we'll have inputs to get to a product. And so the input will oftentimes be a layer, like a raster layer. We'll do some type of processing or some type of tool, and that's going to give us a final product. When we use the Model Builder in GIS to do this diagramming, we'll oftentimes break it up into 3 components. So we'll have an element, and an element can be an input, it can be a tool, or it can be an output. We will have connectors. These are how we actually connect from one input to a tool to an output. And then importantly, we have text labels. And the text labels really become important in the diagram because that's the naming convention of our inputs and outputs. So if we're always, if there's any point in the modeling process where we're unsure where a file is being stored or where a file is being outputted, we can look at the name, double click on the actual file, and we can see the location, and the name should correspond with the text label itself within that particular element. These can get quite lengthy and involved, and it's kind of a good way to keep track of larger GIS projects, and we can certainly replicate GIS projects using a modeling process. So back to suitability. So we use model build in a diagramming sense of process to oftentimes do this thing called suitability analysis. And usually we'll call it MCE, or multi-criteria evaluation. And really what that means is that we're just looking at a series of criteria to determine a location. So it's not so much just one layer that we're interested in. It's several layers, several thematics that are going into a GIS system to create some type of output. An MCE is often used to find suitable land for a specific purpose, and the attributes become really important. And we're going to talk about 2 different attributes or characteristics that we oftentimes create suitability, by which we create suitability. We do it through 2 different procedures. So we're familiar with Boolean Logic. We used it when we were doing the analysis for Kosovo. And there's also what's called a weighted linear combination. So the difference between the two, in Boolean, we're just talking about a 0 and a 1, a true or a false, or either or. It's a very black and white type of math. Whereas in weighted linear combination, what we're doing is we're giving weight to one variable or one thematic versus another one. So, for instance, say I was doing mapping for, let's just throw this out as an example, for beaver habitats. Obviously, being close to a water source like a river or a stream is going to be really important for beaver habitats because beavers need to be close to water. So we would weight that particular thematic higher over, say, distance from roads or maybe a certain type of land cover or tree cover. Water becomes really critical to a beaver environment, so we're gonna weight that particular thematic higher. So that would be an instance of a weighted linear combination. Whereas Boolean, we're not giving any special weight to water. We're just putting water into the larger equation with roads and tree cover or land cover and just running it. And so this upcoming week, we're just going to be using strictly Boolean overlays. These operators are based on a very old math, relatively speaking, that was developed in 1854 by George Boole. In a book called An Investigation of the Laws of Thought. And so this is a math that has been around for quite a long time and is very powerful in GIS and oftentimes utilized. And we kind of know from Kosovo how this works. So we have several different equations that we can run in overlays. So we can do things like intersects and unions. We can do clipping. We can do joins. We can do proximity analysis, and those things are all fall within the notion of a Boolean logic. So when we were doing MCE, or suitability analysis, multi-criteria evaluation, we're going to use two different types of operators. We're going to approach these spatial problems two different ways. One's spatial and the other one's logical. So we need to know the difference between the two. And intuitively we know this difference because we've been using it quite a bit. We just haven't really named it yet. So we're going to name it now so we can understand it a little bit better. So when we set up criteria, say we're trying to cite something, we're trying to find a parcel that fits a certain type of criteria, we can think spatially and logically. And let's look at the examples for spatial versus logical. So for spatial, we would say, this is just a fictitious criteria, a site must be outside of a flood zone. So that makes sense that we don't want to be in a flood zone if we're trying to develop a new property. That would be a spatial query. It's all based on whether or not the particular location is within another thing. And as we know, that's a spatial question. We could say also that the site must be vacant. That's a quality of the actual attributes of our feature. So in that case, that's a logical expression. That's not really about a spatial property per se. That's more of an attribute, more of a quality. In that case, that's a logical instance. And with spatial operators, we oftentimes think of those in terms of proximity. So as soon as we start seeing within a certain distance or inside versus outside, those are definitely spatial operator type of queries. Now, logical operators, we know those by things in SQL when we're working in an attribute table where we say equal to, greater than or less than. Those logical operators that we find in SQL in the attribute table really give away the fact that it's a logical operation that we're doing. And when we do these logical operators, we're oftentimes using thresholds and ranges of values, especially with logical selections. And a threshold value versus a range of values can be described as everything up to a certain value or past a certain value. That's a threshold. So if I want to say I want to get all slope that is greater than 2 degrees. My threshold value is 2 degrees. Whereas if I want to say I want to get all slope within 2 degrees and 7 degrees, that's a range of values. So between 2 and 7, we basically have 2, 3, 4, 5, 6, and 7 degrees as possible candidates. That, of course, is a range of values. So we're really, especially with logical, we're only dealing with those two categories, either a threshold or a range of values. Now, the order and sequence of spatial versus logical in suitability analysis is not particularly important, but usually we'll run the logical queries before we do the spatial queries. That's the typical process. Okay, so we can get to, here's two processes that are getting to the same result. So on the top, we're selecting parcels that are vacant, and then within 1 mile of a highway, and then that are outside of a flood zone. And we can see our final on the right side is exactly the same parcels as the bottom process. Now the bottom process starts with picking parcels that are outside of a flood zone, then we go to within 1 mile, and then are vacant. So on the bottom one, we're doing our spatial queries first and then tacking on a logical at the end. In the first one, we're doing a logical, and then we're doing a spatial and a spatial query. So we're just changing who comes first, logical or spatial, but we're getting to the same result. Okay, we're getting to these particular parcels. Now, NCE can happen in both vector and raster models. Okay, and oftentimes we'll use vector to a certain point in our modeling process, and then we'll use rasters. Or we'll bring the two together. And remember, we can convert between raster and vector. We can go back and forth between the two models. That's not a problem. As long as they're in the same coordinate system and everything overlays correctly, we can do transformations between the two models perfectly fine. Let's talk about vector a little bit. So with vector, usually what we're doing in MCE is we're simply going to take our layers of information in vector format, and then we're going to bring those together into one final layer. And we usually will use a union process, and we've done that in the past in this class, where we bring several layers together through a union geospatial process. And what happens when we do that is that we're going to have a mixture of polygons as a result. So in our example here, our visual example, I don't know exactly what these layers are, but I'm just going to take a quick guess. So the first one might be slope. The second one looks to me like land cover. The third one might be areas that are inside and outside of a flood zone. And then the last one might be, say, a road buffer. And we bring all those together. When we bring those together, there's something within those four thematics that we're interested in. So there's some query that we're particularly interested in. So let's make one up. This is just fictitious. I don't know if it's actually the real one. Let's say that we want to find suitable locations that are within a certain slope. Okay, they have a certain rise to them. They're within a certain type of tree cover. I want them to be close to pine trees or pine tree areas. I want them to be outside of a flood zone, and I want them to be away from a road by, say, a mile. So all those characteristics, those multi-criteria specifications that are thematic, those can come into the final overlay union, and I can select out of that final overlay union exactly the criteria that I want, the very specific criteria. And so actually it has it listed out here. So it looks to me like I got my model right on the first slide there. So I had steep slopes or slopes versus land cover. There's a stream buffer instead of floods, and then a highway buffer, the last one, which you can't really see. It's kind of washed out on the screen here. Anyhow, these all go to a union process, which we've done and is easy to do. And what we're looking for is we're just looking for the combined features, the combined layer, and then we can select out of that attribute table exactly what we want. Okay, the new polygons have the attributes of all the source layers, and then we just pick out the combination that we're really interested in and get rid of everything else. And so we can see here in this case we have three that we've added together, we've unioned together, and then we have this final area right here that in this case we're interested in for some specific reason. Okay, so suitability is a way to get to something that's suitable in our criteria. When we do this in vectors, sometimes we'll get what are called slivers. And slivers, because we have a lot of different layers that are being kind of smashed together, they're these little pieces of residual polygons that don't really have a lot of value because they're so small. We would never use them as a final result to be very meaningful because they're just too small. So what we can do is we can tell the GIS, listen, put the slivers that result from our overlay process into the polygons that are adjacent or that are close to the slivers. Okay, so we're basically going to give over area that is pretty close to the criteria that we want to meet, and we're just going to kind of get rid of those little teeny tiny pieces of resulting land that aren't going to be big enough to do much of anything with, and we'll give those over to another polygon. Now in Raster, we can do a very similar process. So we're not changing the overall model of suitability, but we are changing the inputs, the actual model cell-based versus vector-based approach. And what really becomes critical in Raster again is that we're doing analysis at the cell level. So the cells have to overlay, and the cell size becomes very important between one raster to another raster. So I want to make sure that I'm doing analysis at my cell level that is consistent. So if I have elevation that's at 30 meters and I want to derive slope, and then I want to use a land cover, I need to make sure everything's in 30 meters. And we can change the cell size in one raster to another raster. You just need to make sure before you do the final analysis process that you have everything in the correct coordinate system, and they have the same cell size from one raster to another raster. If we have that condition met, then we have cells that overlay correctly from one to another, and we can create a calculation between those cells within the rasters. I'm going to skip this this slide here. I think this is a little bit more meaningful slide. So if we simply add these together, so very much like the process of a union and vector, if we have one raster that has values thematically for something, then we have another raster that has values thematically for another category, and then a third for the final, and we add those together, we're going to get final values. And those final values are basically a combination of everything that's coming into our model, into our raster multi-criteria evaluation model. Okay, so oftentimes it's just simply a process of addition. And we can see that here in this slide. So if our first input raster in the top left-hand cell is 3, and then we add it to the next one, which is 11, we're going to get an output of 14. Okay, so that makes sense. And what's really critical is just remember, we're doing our calculations at a cell level, and this final cell value, that's what's really important to us. We can do this through two different processes. We can do raster query or a raster combine, and they're very similar. So with a query, what we're going to do is we're going to have our inputs, and they're going to go to, say, a query tool, and then that's going to give us a suitable location. And when you do these queries, these sequential queries, the layer created by the first query is used for the second query, and so on. Okay? So another process that we can do is do raster combine. And raster combine, I think probably takes a little bit longer, but I think the steps are very clear as to what's happening. So let's walk through this process. So if we have an input of steep slopes, then we have an input of land cover, distance to streams, and distance from highways. Those have many different values. Okay, so in the first, let's look at land cover here. So we can see it looks like 1, 2, 3, 4 different colors. We have a yellow, a dark green, a medium green, and a light green. Those are all different values within that land raster. We can reclassify those to Boolean, to 0 versus 1 through a reclassify, and we've done reclassify. That's going to give us a binary or a Boolean land cover. It's going to be either a 0 or a 1 value. So it looks here in our binary land cover value for this particular model, what they probably wanted was this area that is the yellow color. So that was the suitable location, so that looks to me like that's gone to 1, and the dark green is everything else. That's going to be our 0. So up here we've gone from many different slope values, reclassified into the range or the threshold value that we want, and that gives us a 0 and a 1 as an output for suitable or unsuitable for 0 and suitable for 1. Same thing with distance to streams. We take a very complicated values, reclassify those, make those simple Boolean, and then we just bring those together through a final combination or simple overlay. And the result is going to give us, very important, it's going to give us at the cell level certain results. Okay, so in this case we're going to have a slope code, a land cover code, a stream distance code, and a highway code. And we can see over here when we bring those all together, we're going to have a codes in an attribute table through this process, and we're going to have a final cell value that we're looking for. In this case it's going to be the green. We can see the green right there, and it looks like green is number 2. That's the value, that's what we're looking for. And we can simply reclassify that final result to say 2s are now 1 for our suitability and everything else is a 0. So we get a Boolean suitable location, and that's kind of what we're after. We're after for a really simple yes it's suitable or no it's not suitable based on a series of criteria, multiple criteria going to a very simple result. And this week the whole assignment is based on bringing a lot of criteria into the system, into the GIS, and deriving a simple result of it's either suitable or it's not suitable. So let's take a look at our assignment in detail before we actually start that assignment. So what we'll be doing this week is we're going to be citing refugee camps or suitable locations for refugee camps based on a series of criteria coming into our GIS. And this is taking place in Uganda in a district called Gulu. And the book this week, the assignment, will walk through kind of why the criteria has been chosen and give you a context for the assignment itself. But what I want to do right now is I want to go through just the basic criteria itself. So the first thing we're going to be working with is digital elevation, and we're going to be deriving slope. So we need to make sure that we just have just enough slope to ensure that we're going to get drainage in real rainy seasons. So that particular calculation is a range of values. It's not a threshold, it's a range, and the range is from 2 to 7 degrees. That's what we want. Everything above 7 degrees slope we want to get rid of. We're going to call that 0, unsuitable, and everything below 2 is going to be unsuitable also. So we're going to have a final Boolean result. 2 to 7 is going to be our 1 value, and everything else is going to be a 0 value. So that's going to be our first Boolean. Second one is the camp location, it needs to be close to a road. Okay, it has to have some proximity to a major road, because if we aren't close to a major road, there's no way that we can develop the camp, that we can produce a delivery of assistance. If it's just out far away from any transportation network, that's not going to work out for our camps. So we need to have them be within a certain proximity. So what's happening as we go along this model is we're starting out with basically any location within the Gulu district is going to be appropriate. And then we just start going through this winnowing down process. So we're going from large spaces to little teeny tiny spaces as we walk through our criteria. So it's a process of winnowing down, of making space restricted to certain criteria. Next one is going to be close to a market. So we want to be somewhat close to places where commerce is taking place, where people can actually buy things. So being close to a market allows the camp to just operate better in general, and it offers people that are within the refugee camp possibility of some connection with a larger economic structure. So we want to be close to a market. So now we've added a third criteria that's making our possible space even more restricted. And like Kosovo, we want to make sure, especially in war-torn regions, that we're as far away as possible from potential locations that we know have a lot of ERW, have a lot of remnants of war, explosive remnants, have any type of risk that's war-based to the population that we're trying to house, the refugee population. So we want to be away from UXO. So once again, we're restricting that much farther. So now we're getting down to really teeny tiny little places in our Gulu district, our larger district. And the final one is that we want to be outside of really dense urban areas, because siting a refugee camp in a dense urban area, we just can't find a parcel because it's already dense. All parcels are already taken. Those are going to be unacceptable. So we need to get rid of urban areas. So the last couple criteria, you're going to actually we can see that those are away versus close and close. So with slope and being close to something, those are going to be things where we're doing proximity buffers, and we're going to say that they're within these things. When we get to the last two, where we're taking things away, we're going to be using a clipping procedure to do that. So the tool that we're going to use in geoprocessing is a clipping tool, whereas the first ones are going to be proximity queries based on buffers. And this is going to give us, through these 5 criteria, it's going to give us our suitable campsite locations. So that's going to be the final result of our assignment this upcoming week, our suitable locations within Gulu where we could potentially site a camp. And then you're going to go through a very final step where you actually calculate capacity density. So what areas would be appropriate for creating capacity, and I believe it's between 10,000 and 20,000 persons. So we want to find areas that can have a carrying capacity between 10 and 20,000. So we want to get rid of real small areas, and then also ones that are just way too big. We want to kind of restrict the area a little bit there. So that's kind of suitability analysis in a nutshell, and hopefully this lecture gives you an overview of some of the processes that we can do. We can do it both in vector and raster, and we're starting with a lot of information coming into the GIS, and we're getting to a final simple result that is either suitable or unsuitable. So the whole process of suitability is going from a very complex thematic structure across many layers of geospatial data, and we're winnowing it down through the GIS to just a very Boolean, yes, this area is suitable, or no, it's unsuitable. Okay, so good luck this week, and hopefully this lecture was helpful in understanding suitability.